Hi, this is Steve at Allied Scientific Pro. Today we'll demonstrate the single event effect testing in our lab. So you're welcome to come to our lab to do some testing. And so we'll demonstrate two devices under test with the laser. So we'll demonstrate some of the effect. So you can come in the lab now.
Hello, my name is Yu-Hao Chu, a photonics engineer at Allied Scientific Pro. So I will give a system overview of our SEE laser testing workstation. So we will also, in this demo, try to achieve single event effects using our integrated circuits. So first we have the laser. We have a picosecond laser with 30 picosecond pulse width and adjustable pulse frequency. And after that, we also have femtosecond lasers for our other workstations for single photon absorption and two photon absorption. Next we have our motion control system. So here we have X, Y, and Z control where we can position the integrated circuits and scan the chip for single event effects. So we have piezo controllers with nanometer precision to precisely position the chip in the X, Y, and Z direction. After that we have the optical system, which guides the laser beam, and this includes polarizers to precisely tune the pulse energy of the laser. And we also have two objectives which are used to focus the laser beam. So installed in our system currently is the 20 times objective to focus the beam on the chip. And we also have here the 100x objective to get a more deeper focus into the chip. We also have two imaging systems included in our SEE workstation. The first is visible wavelength imaging to see the chip, and the second we also have shortwave infrared imaging system, and including that we have the infrared LED to illuminate the chip. So you can see here on our screen we have images of the SRAM chip, and I can adjust the focus so that the focus of the Z stage to get a better focus. And we also have a laser control interface to adjust the pulse frequency and the pulse shape, and our polarizer interface to adjust the pulse energy, and as well as our LabVIEW program for controlling the stages and the scanning. So next, Rez will explain the chips that we are testing today.
Thank you.
Hello, my name is Rez Mania. I'm the application scientist for Allied Scientific Pro. And after Yuao's introduction, I will introduce the chips that are under test, or device under test. I have to mention that we are using a near-infrared laser at 1030 nanometer for doing these testing. So the first chip that we'll be testing is a SRAM with a 64 by 64 pixel matrix, and basically this is mounted on an Arduino board where we could write a 1 or 0 to different cells. So we would first of all write a 1 to all the cells, and then we will illuminate the chip with the laser beam and show that some of the cells have changed their state from 1 to 0. This particular chip has been tested before by many of the pioneers of the field, and they have already demonstrated the existence of single event upset and single event functional interrupt in it. So the data is all in the literature, and we are just showing that we can also get it with our laser system. So in order to do that, the first step would be for us to start with our Arduino board, and I'm just going to start the software here our Arduino software to write a 1. And we have a box there that could choose between read and write, or writing a 1, writing a 0. There's switches and buttons there. So the first step would be to write a 1 to all the 4096 cells of the SRAM. So we're just waiting for this Arduino software to open, and as soon as it opens, we start writing the 1. Yes, it's right there. So all I do is I would just start a serial monitor. So it's a serial monitor, and then yeah, this is right here. Just there, tools, serial monitor. Okay, so there it is. This is the serial monitor, and then he will press a button which would start writing 1 to all the cells. So right now it's just writing. After the writing, we'll have to do a reading to make sure that all the cells have a value of 1. So just give it a minute. It typically takes about a minute to write these. So in the meantime, I will show the SRAM. This is one of our previous chips that we used before, and you can see it's been decapsulated. It has a ceramic cover that was taken off, and you can see the chip, which is uncovered there. And it's a 64 by 64 array. The size of each cell is about 100 micron. So this is done. This is done. It's writing, and now I'm just going to clear the output, and he's going to read it. By switching a button, we will read it. So press the button, please. So it should be all 1 right now. So the value of Q that you see over here is 1. That shows the output. And every cell is 1. So it has to go through its iteration and write to the 4096. And then we will check that. We will check to make sure everything is 1. After it's doing its reading, we'll check that everything is 1. Yes, so I will copy this, Control A, Control C, and I'll copy this in Notepad, Control V. And then I will just check to see if all the values are 1. Indeed, is there any zeros anywhere? So I will just do a search, and first look at Q equal to 1, Control V, and we can find 1s easily. But what about 0? Are there any zeros in this? And it says no, cannot find Q equal to 0. So that proves that all the values right now written is a 1. So at this point, we're going to put our laser goggles, and we're going to shoot the laser, which has a typical of about 100 micron beam size, because we are using the 20 times microscope objective. It's not so narrow. And we are going to do a spiral scan and going over 4 lines with this LabVIEW program. So basically going along the spiral along 4 lines.
Pattern, right?
Yeah.
The chip is being moved to the right by 20 steps, and then it will move downwards by 3 steps.
You have to mention that the step size for the scan is 20 micron, and it's moving 30 steps along one direction laterally, and then goes up by 3 steps, and then moves in the opposite direction by 30 steps. and this way it will complete the serpentine motion. So and then we will look at the results. So the laser is firing on those cells at the same time that this is moving. So we are on the second, the third?
The second row. We're on the second row. So we'll do 3 rows of scanning?
Yes.
Okay. So now we're going down by 3 steps. We will begin the 3rd row. This is now our 3rd row. Now we go back to the right. We just completed its 3rd row. I'll stop the scan and I'll stop the laser. So now we're going to read the cells on the SRAM, and simply I just have to start the read with our circuit.
Yeah, if you can show the screen right now. So we are looking for occurrence of zeros, which may not be obvious at the first glance, but we will do a proper search later to see if we could find any zeros. You know, you can see actually some zeros appeared there. So those are the upsets. And we will just do a mapping of these zeros to see where these upsets occur. So these zeros could be either due to a single event upset, or it could be due to single event functional interrupt. One of the two. And the pattern that we observe will tell us which one it will be. So let us just wait till it finishes. It's almost done. 3,200. So it has to go up to 4,096. And then we would look at the file. Alright, so at this point I'm going to copy this into a notepad file. So Control A, Control C, and then I'm going to copy this in a notepad file. Control V. And I will save it as today's date, which is October 7. So save as, and then we will read that using a LabVIEW program that will show us where this upset has happened. So we are saving it. Yes. So I'm just going to call it October 7 SRAM. October 7 SRAM. And save that. And then we would just go to our LabVIEW VI here. This is our first one. And I will select this file. It's October 7 SRAM. And then I will run it. So that will extract all the values there, and then it will tell us where. Run it, and let's look at the matrix. So this is the whole 64 by 64 matrix, and let's see where are the zeros. Yeah, you can see there are a whole lot of zeros in this area. Over here you can see all these have turned into 0. All the ones have turned into 0, and that is not so localized. It's like everywhere. So, and if you go further down, you also see another sets of zeros. So because there's so many zeros, there's so many cells, we haven't even shone the laser beam on these cells and they have turned into 0. That's a clear indication of a Cepheid effect. It's not a SCU, because if it was an SCU, the occurrence of zeros would be in a localized space. And we even tried before with a similar experiment to try to write a 1 to all these cells, and it wouldn't write. And the only way we could get it to write was to disconnect the cable and reboot the system, and then after that it was able to write the ones. So that's just clearly a Cepheid effect. And we can also have a color plot of that. If you want to see a color plot of that, I can show you. So we'll just go here and select that file. Yes. So this is like October, and the name of the file was October 7 SRAM, and we would just run it. And all the blue ones would be showing the locations of the, yeah, there you go. So you can see this is the whole 64 by 64, and all the ones that are dark blue are the zeros. And there are almost, I would say, 1,000, more than 1,000 cells that have turned into zero. And that shows the occurrence of Cepheid. So I was explaining that we did also get the SCU, where you only get the upset in a limited number of cells in a localized space. And here I have a demonstration of that. This is from a previous measurement. You can see these blue show only 8 cells that were upset. And we got that with the 100 times microscope objective. Right now we are getting it 20 times. So for the 100 times, the power level would be less, and it will be more focused. This beam size will be smaller. So after this demonstration, I think we are done with the SRAM, and now we could move on to the op-amp LM124, which is another device that we are testing, and this has also been tested by many of the pioneers of the field in the past. And this particular op-amp has some sensitive transistors, including one transistor called Q9, which when a laser is shown on this transistor, it turns on and then it will show some pulses. So we will just see the plot of the transistor on the camera, and then we would shine the laser on it, and then we look at the oscilloscope to see where the pulses are. So you're always doing the adjustment. The oscilloscope, in the meantime, I should mention that
we can see here,
yes,
the as we get a better focus using the piezo stage, we can see the zoom in of the op-amp, and so we're looking for the Q9 transistor. So this region right here is the Q9 transistor. We've been able to locate the exact position of the sensitive cells.
I also have to mention that we are externally triggering the scope using the laser, a sync voltage from the laser. So that is being triggering the scope at 10 kilohertz. And then we would look for these pulses when he shines the laser on that sensitive transistor. So let us know when you are firing.
Okay, are you ready, Rez?
Yes.
Alright, so I'm going to start the laser emission on the sensitive nodes. And we will observe the SET on the oscilloscope.
So let me know when the laser is actually shining.
It's shining.
So this, yeah, you see the drop in voltage, and this is the line that we are looking at. We are looking for set pulses. When he's shining, he's moving the beam around so that it shines on that transistor Q9, and we are just waiting for these pulses to appear. What's going on right now? And there is it. There's the first pulse that happened. That's our set pulse. So here's the second pulse, and there may be more pulses. So at the moment there are no pulses, but we definitely saw 2 pulses, and this is the third pulse. So I think that's enough to prove that we were able to see set pulses when we shine the 1030 nanometer 30 picosecond laser beam of a dimension of 100 micron on the sensitive transistor Q9. And this concludes our demonstration. This lab is open for other testing for MOSFETs, power MOSFETs, or FPGAs, or any other type of device. And these two devices, we chose them because they were known information in the literature about the occurrence of the SCE effect. Thank you very much.